This conference will now be recorded.
Hello everyone. We are starting a new chapter which is hydrogen. So the topics we will cover today: introduction, position of hydrogen in periodic table, resemblance with alkali metals and resemblance with halogen, then ortho and para hydrogen, preparation of hydrogen, and if we still have time we can also see commercial production of hydrogen and properties of hydrogen. So as the introduction for this chapter, that is hydrogen, or you can also call it dihydrogen, because in the elemental form it remains like this type of diatomic molecule. That means two hydrogen atom, there will be a covalent bond between two hydrogen atom, and it exists, that is the natural existence is like this type of diatomic form. So that is why it is also called dihydrogen, but mostly we call it hydrogen. Now if you look at this picture right hand side, this is the elemental, that is sign we use for hydrogen. It is the first element of the periodic table, and this is flammable gaseous substance, and it is the first member, and that is why it is the simplest member. And as it is the simplest member, it is having one electron and one proton in the center, in the nucleus, right? So as it is having only one proton, so atomic number is 1, and that is what is the first member. And then its element name is hydrogen, but we, that is in daily life, we also call it hydrogen for the H2, that is diatomic form also. So dihydrogen, hydrogen, both terms are used for the same reason. And its atomic weight is 1.008, but sometimes for calculation we ignore this 8 and simply we consider it as 1. Although this is the most abundant element in the universe. So if you consider from the point of view of universe, not only our Earth, there are other planets also, then it makes only about 0, that is it is abundant in universe point of view, but if you consider only Earth crust, then it is very low amount. In the Earth crust it is only 0.14%. Fine. It is present in most of the compounds that we see in our daily life, such as water, carbohydrate, protein. So carbohydrate, protein, these two are basically organic molecules. So whenever we consider organic chemistry, we know it is all about carbon. And after carbon, the next element that we consider mostly in organic chemistry, it is basically hydrogen. So carbon and hydrogen, this is present frequent, that is the most common in the organic chemistry. And as carbohydrate, protein, these two are also organic molecule. Carbohydrate, there is presence of carbon, hydrogen, oxygen, these three elements. So hydrogen is also present in that. Then proteins, which is basically polymeric in nature, where the basic unit, that is the monomeric form, is basically amino acid, and there also hydrogen is present. So these are the compounds, some of the examples of compounds that we see in our daily life where hydrogen is present. Now hydrogen, there is not only one proton, but there is also one electron, just one electron is there. So if we consider the nucleus, there is one electron and there is one proton. So this is outside, but in the nucleus there is one proton. Okay, and as it is having unpaired electron, so that is why it is very reactive, and it does not occur in the atomic form. So this is the atomic form. If you simply write one hydrogen, it is basically the atomic form, but it remains in the diatomic form, because if you simply consider one single atom of hydrogen, there is only one electron. So when both the electrons, they are now pairing together, they are making a covalent bond, then there is formation of hydrogen, that is the diatomic form of hydrogen. So single hydrogen atom, this is the nucleus, only one electron, and another hydrogen, they are combining together, now they are sharing this electron. So in this way there is formation of a single bond where one pair of electron is present. Fine. Now why there is separate chapter based on hydrogen? There must be some significance for it. So that is why here we have there is a separate chapter for it. It has great industrial importance, and also the most important application point of view, if you consider, then it is the major future source of energy. So as we will proceed through this chapter and we will reach the application part, there you will see that from hydrogen it can be a good source of energy in the future, though nowadays it is not the major source we are using as energy, but in future there is a potential for that, and as it can overcome the global concern related to energy. Because if we consider pollution nowadays, the energy source that we use, there is a chance of production of pollution is high, but when we use hydrogen gas as the source of energy, that problem is solved. So that is why it may be a good source of energy, but there are still some processes that we have to consider, for which it is still not the active, that is we are not still using it in the active form, because of some there are some things that we still have to overcome. Okay, but there is a chance that we will be able to use it in future as a major source of energy, because the chance of pollution is very less compared to the other fuels that we use nowadays. So this is the introduction for hydrogen. Next we will see its position in the periodic table. Now this is the only element whose position in the periodic table it is very controversial. And why it is controversial? The reason behind that, when we place hydrogen in the periodic table, obviously it is based on atomic number, but according to that it should be placed with the alkali metals, that is in the left hand side extreme. But still there is some controversy, and why it is so, that we will see here. So you will see when a periodic table we see in different places, the position, sometimes hydrogen it is written in the left hand side with alkali metal, sometimes it is written in the middle part. Okay, so that is why there is controversy in different places. Its position is not fixed. Now why it is so, that we have to see. This is the first element that we know, and if you consider only the periodic table, forget about hydrogen, just periodic table, we know that all the metals they are present in the left hand side of the periodic table, and all the non-metals they are present in the right hand side of the periodic table. Remember, in the right hand side we have group 17, where all the, that is most non-metallic elements are present. I'm talking about halogens. And metals, they are situated on the left hand side. Remember about this block, where group 1, group 2 metals, sodium, potassium, calcium, lithium, all these elements, alkali, alkaline earth metal, they are present in the left extreme. So we can say that as we are moving from left hand side to right hand side, metallic character is decreasing. And if you consider the middle part, the elements on the extreme right, they are non-metals, and mostly in the middle part there is some metalloids are present, which are having properties that are both like metals as well as non-metals. But what about hydrogen? Metalloids, non-metals, everything is fine, but what about hydrogen? The only exception to this rule is hydrogen. So that is why the problem, how this problem arises, this is the reason. So see, sometimes hydrogen it is placed just above the alkali metal, so this is basically group 1, and sometimes if you consider its that is resemblance in properties, it has resemblance in properties both with halogen as well as alkali metals. So that is why from the resemblance, if you simply consider that it has some resemblance in the property, then it is in the group 17 sometimes, but mostly we place it in the middle, because it has though it has similarity with alkali metals as well as the halogens, but it also has some dissimilarities both with alkali metals as well as halogen. So there is some resemblance with alkali metals. Different periodic table use different positions of hydrogen. There is also resemblance with in properties with halogens, and this is the compromised position. So it is not in the left extreme, it is not in the right extreme. Now we have placed it in the middle. So what are the similarities it has with alkali metals, that is group 1, and also with halogens, that is group 17, left extreme, right extreme, that we'll see in the next slide. Resemblance of hydrogen with alkali metals. So when we consider alkali metals, this is the general electronic configuration, NS1. For example, if I write sodium, it has general electronic configuration 3s1. If I write potassium, it has general electronic configuration 4s1. And before that, there is presence of noble gas configuration. So I'm simply writing the outermost electronic configuration. Now, if you consider the electronic configuration of hydrogen, it is basically 1s1. That is the simplest. And it has some similarity with the general valential configuration of alkali metals, because that is also ns1. Only difference is before 1 is there is no noble gas. But in case of alkali metals, this is the outermost valential configuration. But before that, I am writing here noble gas configuration. So for sodium, as it has that is atomic number, remember it is 11. So the previous noble gas is neon. So when it is potassium, atomic number 19, the previous noble gas is argon. So depending on which period you are considering, sodium is third period, potassium is fourth period, depending on different noble gases will be placed. But if you simply consider only the outermost electronic configuration, then it has similarity, right? So this is the first point for similarity. Then the second point, similarity, it forms unipositive ion. So we know that on the oxidation state that is possible for group 1 alkali metals, it is +1. You will never see sodium 2 plus, sodium 3 plus, or sodium having any negative charge. The only oxidation state possible is +1. Why? Because as the general electronic configuration is like this, it will always try to, that is this electron, there is a tendency to loss. Why? Because when this electron will be lost, it will reach the noble gas configuration, which is stable configuration, and any system always try to reach noble gas configuration. So that is why there is a tendency to donate this electron to some other species. Now what will happen? If it is so, obviously the oxidation state is plus. But what about hydrogen? In case of hydrogen also, once it is giving this electron, it is achieving the that is, it is forming the ion H plus, unipositive ion. So it has similarity from that point of view. Cesium plus, sodium plus, K plus, we know this type of ions we get for alkali metals. This is the second point for resemblance. Hydrogen from halides which is having formula like HX. So X may be F, Cl, Br or I. HAF, Cl, H, Br, H. Then when you consider oxide of hydrogen, it is basically water. Another oxide is also there, which is H2O2. So the formulas, if you see, 2 hydrogen, 1 oxygen, 2 hydrogen, 2 oxygen. Now if you consider alkali metals, they also form halides having same type of formula, HX. Now if you consider potassium, that is KX, or it may be NaX, then lithium X, X is any halogen. So there is similarity in the formula. Then oxide, that is water, is basically oxide of hydrogen. You can find similarity with Li2O, though it is true that different alkali metals they form different types of oxide. For example, when it is lithium, you will find similarity in formula with H2O. And when it is sodium, it mainly forms peroxide type of oxide. There are basically 3 types of oxide you can observe for alkali metals. One is normal oxide, which you can call monoxide. Then there is peroxide, which is mainly observed for sodium. And then there is, as you are moving down the group, for example, potassium, that is the size is increasing, then there is a chance of forming superoxide. That example here not present because only these 2 formulas you can find similarity. For example, Li2O and Na2O2, 2 sodium, 2 oxygen, 2 hydrogen, 2 oxygen. So there is similarity. Then if you consider sulfide, same type of formula just like H2O, only in place of oxygen we have sulfur. But formula is H2S. Similarly, similar type of compound you can also get from sodium. So this is, see, the formula is 2 sodium, 1 sulfur. And in case of H2S, it is 2 hydrogen, 1 sulfur. So there is similarity in the formula. Okay. It acts as a reducing agent just like alkali metal. So these are the some of the properties that you can find similar for hydrogen as well as alkali metals. But similarity is not, there is also dissimilarity. Next that we will see. However, unlike alkali metals, their ionization energy values, if you see, this is in this range 377 to 520. Obviously, as you are moving down the group, lithium, sodium, potassium, this value will decrease. Ionization energy means the energy that you have to provide to remove the most loosely held electron. So in this case, it is this electron, ns1 electron, that you are moving. But when it is hydrogen, look at the value. It is far greater than this range. So this is the difference. Now why it is so, this difference we are observing? Because hydrogen atom is very small. Now what will happen when you are trying to, suppose this is a proton, it is present in the nucleus, and you are trying to remove this electron, the distance with the nucleus is very small. So removal of this electron is not so easy. But when you consider alkali metals, basically in between this nucleus electron, in that is in this middle portion, there is also other shells and with electrons, so there will be some screening effect, but that is not present in case of hydrogen. So the size is very small, so removal of electron, that will not be very easy. It is very close to nucleus. So that is why this type of difference in ionization energy value. And not just this ionization energy, there are some different, because of this size difference, we know atomic properties, they are that is directly related to the size. So when size varies, obviously there will be difference. So hydrogen atom, as it is very small in size, many properties of hydrogen, not just ionization energy, it will be different with alkali metals. From another point of view also, you can say that as this ionization energy value is so different, so obviously it will have direct effect on the chemical property. And this is the reason, though there are some similarities, but because of this dissimilarity, you will see that hydrogen is never included in the discussion of alkali metal properties. There is a separate unit for S block, which is probably unit, that is the next unit, unit 10. In that block, we discuss group 1 and group 2, that is alkali metals and alkaline earth metals. But when these groups are, that is this group 1 will be discussed, there you will not find that hydrogen is also included. So for hydrogen, we have separate chapter. It is never discussed with S block elements, that is group 1 elements. Okay. Next is resemblance of hydrogen with halogens. Like formation of halides, we know halogens, if you consider its electronic configuration, general electronic configuration, after noble gas, it is basically NH2 NP5. Fine. Now when it is accepting one more electron, basically it is reaching the next noble gas configuration, NH2 NP6. That means there is a tendency for halogen, I'm writing in general, X, it may be any halogen, there is a tendency to accept electron and to convert to X negative, that is anion formation tendency is there. Now same type of observation you can also see in case of hydrogen. So hydrogen also, it can accept one electron and it can form H minus. Now what is the driving force behind that? Hydrogen is having configuration 1s1, and when it is accepting electron, it is forming H minus. Now the configuration will change to 1s2, and this is basically the configuration of helium, that is the next element after hydrogen. But 1s1 and 1s2, when it is 1s2, it is fully filled configuration, that is the maximum capacity is reached, and that is obviously more stable species, and this is the driving force why hydrogen can also accept electron just like halogen. So now its electronic configuration is to the next noble gas, which is helium. In terms of ionization enthalpy, if we see, this value you have already seen in the last slide. And what about the ionization energy of halogens? This is the range. Now you can find some, there is some, the value is close, it falls in this range, right? In the previous case, you have seen the difference with alkali metals. For alkali metals, the values are so low, but for hydrogen, it is greater than 1000. But in this case, it is close. So this is the resemblance with halogens. But the electron affinity value, if we consider, of hydrogen, it is much less than that of halogen. Now, electron affinity, it is the reverse process of ionization energy. Ionization energy means energy you are providing, you are removing an electron forcefully. But when it is electron affinity, suppose we have any element, I am writing E in general, you are adding one electron and now it is converted to E minus. That means to add one electron forcefully, now the energy, mostly it is negative energy because energy is released. In some cases it may be positive also, but for halogens it is negative because halogens, they are the most non-metallic, group 17. So there is, as we know, move from left hand side to right hand side, this type of tendency to accept electron, that will increase. So that is why for halogens, they are the most negative. That means the process is very facile process. The value of energy is negative means energy is released. It is becoming more stable. That is why energy is released. So electron affinity of halogens are much less. Now when I'm saying less means I'm talking about only the numerical value, not about the sign. But electron affinity, that is the tendency to accept one more electron. If you consider that tendency and if you compare the tendency with the halogens, obviously in case of halogens that tendency is very high. But for hydrogen, this, if you want to add one more electron, though there is a evidence of formation of H minus, but compared to the tendency of electron acceptance, compared to halogens, obviously in this case it is less. So this is the difference between halogens and hydrogen. Hence, tendency of hydrogen to form hydride ion, it is low compared to that of halogen. So it is not that it doesn't form, but the tendency is low. So the more easily you can get X minus from halogen, it is not so easy in case of hydrogen. And if you consider this type of difference, so ultimately what conclusion we are drawing, there is some similarities, dissimilarities present in case of alkali metals, and also there is difference, similarities, dissimilarities, that is also present in case of halogens. So that is why the position of hydrogen, it is controversial, and mostly we place it in the middle of the periodic table. And as it is mentioned in the previous slide that when alkali metals are discussed, hydrogen is never included. Similarly, when halogens are discussed in the P block, that is group 17, then also hydrogen is not included. Fine. Hydrogen has, that is why we are discussing in different chapter. There is a complete different chapter for hydrogen. Isotopes of hydrogen. So what is the definition of isotope? What we mean by isotope? So isotope for an element, if I see, suppose the element, any element E, suppose I am saying it has 2 isotopes or 3 isotopes or 4 isotopes. So what I actually mean by that? So when it is isotope, they will have same atomic number. Now when I am saying same atomic number, that is proton number is same, obviously electron numbers are also same because these two are always same. So in case of hydrogen, it is observed that three different isotopes are there. So one isotope that is the most common is this one, where number of proton in the nucleus, it is basically number of proton is always 1. So that is why atomic number is 1. So number of proton, electron in the second isotope, and the third one, see what is the difference? Proton is always fixed, but number of neutrons are increasing. And when we write symbol, basically what we write? We write the mass number, which is basically summation of P and N, proton and neutron. Mass number we write in this part. So see here, mass number is only 1 proton, so 1 is written. And in general, if I write, it will be like this. Z, so E, suppose E is the element, Z means atomic number, A means mass number. So A is summation of P and N. So in our case, hydrogen is E, 1 is the mass number, because we have only one proton, and in case of Z it is always 1, right? Now in the next case, now it is 2, because now you have 1 proton, 1 neutron. In the third case it is 1 plus 2, so that is why we have written 3. Now it is also expressed as D, and the last one, tritium, that is also expressed as T. H, D and T. So you can write it like this or simply T, both are fine. Protium, that is the most common one, hydrogen basically, H, while we use the formula H, that is in terms of HDT, I'm saying that we use H, basically H you can write for all, but then you have to mention the mass number like this. Otherwise, if you simply use H for all the isotopes, you will not be able to differentiate. So for differentiation, you should mention the mass number. And if you are simply writing HDT, then easily, directly we can understand. So protium is the most predominant form. Look at the percentage, and it is the only isotope where neutron is not present. In other cases, neutron is present. So protium, deuterium, tritium, if we compare, then we will see, sorry, it will be 10 to the power. Sometimes this value is written 10 to the power minus 15. Basically, this value, if you write it trace, that is the best, because in different books, sometimes it is mentioned as minus 16, minus 15, or minus 18. Different values are there. But better you write it at trace. So that is the percentage, relative percentage. This is trace. So this is for protium, this is hydrogen, then D, and this is T. Then relative atomic mass. This is one that we know. After decimal, even if you do not consider those digits, it's okay. So it is basically 1, 2, and 3. That is 1, 2, and 3. Radioactive stability. So hydrogen, we know it is non-radioactive. This is also non-radioactive, but the last one is radioactive. For T half value, it is 12. Next is, now as we have different isotopes, due to existence of these isotopes, when we consider naturally occurring hydrogen, there may be different types of formula. If both the natural hydrogen, how we'll write HH, and then it is basically H2. But suppose one H, it is D, then the compound will be HD. Suppose both are D, it will be D2. There is one H and one T, it will be HT. Both are T, it will be T2. So these are the different possibilities hydrogen can exist. Now deuterium, which is heavier than hydrogen, it is also called heavy hydrogen. It constitutes about, so here you have seen it is 99.985, and for deuterium it is 0.015. So compared to protium, it is obviously very, very low. This is a terrestrial hydrogen and it remains in this form, because we know that natural form is diatomic. There will be two atoms. Now whether these atoms both are H, one is D, another one, different possibilities are there. Okay. And what about tritium? This is radioactive isotope of hydrogen. It occurs only in traces. So see here it is written 1 atom per this. That means 10 to the power minus 80. This is the relative abundance. Better you say trace, because this value it sometimes varies. So relative abundance maximum is for hydrogen. After this it is D, and at last it is T. So this is the order for their abundance. So here you can compare all these different types of physical properties and atomic properties. So atomic mass, this value we have already seen. Number of electron, first electron, then P, then N. That you can see here. Number of electron 1, P is 1, and neutron is not present in protium. 1, 1, 1, 1, 1, 2. Nuclear stability, these two are stable, only the last one is radioactive. So there may be a question that which isotope of hydrogen is radioactive. The answer is tritium. Molecular form, H2D2 T2. This is the abundance. See here it is written 10 - 60. Molar mass, it is just double of this value. Mostly it is double, and though that is the more you go to higher atomic number elements, it is not exactly double. But for hydrogen it is double. In this way you can remember it easily. Then melting point and boiling point, look at the value, they are so low. In Kelvin it is 13.96, so very low. If you convert it to degree centigrade, basically it will be it will be minus 252 something. Okay, and if you convert the boiling point of hydrogen, it will be minus yeah, it is minus 252. This one is minus 259. This is around 253. So this will be so low, negative values. So melting point, boiling point, when we see melting point means what? When it is from solid, it is converted to liquid. That means hydrogen is now in solid and liquid form, and that is possible only when the temperature is very low. And boiling point means from liquid form, now it is uh, changing to the phase gaseous form. So that temperature should be also very low, because in liquid form hydrogen is present. That means the temperature itself is very low. So naturally it is present as gas, and these are the melting and boiling points. For these also you can see there is a little difference, 13, 18, 20. There is slight increase as you are moving from H to D to T. Internuclear distance. Now internuclear distance, it is almost same. Then we have critical temperature. Now critical temperature, that is the temperature above which we cannot liquefy any gas. That temperature is known as critical temperature for that particular gas. So in this case, you can see the critical temperature. Obviously, it is also in Kelvin. That means if you consider it in terms of degree centigrade, obviously the value will be in negative. So only when it is negative, the question of liquefaction arises. Otherwise, it does not arise. Fine. Then we have enthalpy of dissociation. Now this value, notice it very carefully. Why I am saying it carefully? Because for hydrogen the value is 435.9. So that is around 434. It is in kilojoule per mole. But when it is D2, now the value from 435 it is increased to 443, and when it is T2 the value is even increased. Now because of this type of value, if you compare, to break HH bond it will be comparatively easy than to break DD bond. That means same energy we are not providing. So it means what? When we are not providing same energy, that means in this case more energy we have to provide. So to break the DD bond it is comparatively difficult, and in case of T2 it is more difficult. Okay, next we will see that is what conclusion we can draw since the isotope have the same electronic configuration. So in all cases electronic configuration there is obviously no change, because we are talking about isotope, and isotope is all about same atomic number, only neutron number is different. That is the definition. So as electronic configuration is same, chemical properties will also be same, and it is not just for hydrogen isotope, it is true for any elements isotope, because chemical properties is all about electronic configuration. The only difference observed is in their rate of reaction. So when you consider the rate of reaction, suppose you are doing one reaction where you have taken H2, you are doing another reaction where instead of taking H2 you have taken D2. So obviously rate of reaction will be different. Chemically they will behave similar way, but rate, that is kinetics, that will be different. Why? Because kinetics is related to this enthalpy of dissociation. As it is easier to break HH bond compared to break DD bond, so obviously reaction rate will be different. Physical properties differ considerably due to their large mass difference. So not only this enthalpy of dissociation, based on molar mass also there are some physical properties that are highly dependent. When molar mass increases, boiling point, melting point, these also increases, which you can see from this table. So as their molar mass is different, because Newton number is different, so molar mass will also be different. So this is 2, 4, 6. It is increasing from H to D to T. So these conclusions we can draw from this table. From that is chemical property same, but the rate with which it will react, that rate is not same, because their bond dissociation enthalpy is not same. And as atomic mass is not same, physical properties will also be different. Ortho and para hydrogen. Next we have this term, ortho and para hydrogen. Now this is all about, that is, you have to focus on the nucleus. If you simply consider hydrogen atom, you need 2 hydrogen atom when you are making this H2 molecule. Now depending on the spin of this nuclei of individual hydrogen, that is the direction, whether this is in the same direction or in the opposite direction, depending on that, we can have 2 different types of molecular hydrogen. Why I am saying molecular hydrogen? Once you are having H2, that is a diatomic form, obviously now it is a molecular hydrogen. It is no longer single hydrogen atom. So here we have 1 hydrogen atom, suppose hydrogen number 1, hydrogen number 2. You can see here both the spin direction, they are on the same side for the proton. So that is why it is called parallel spin, and they are also known as ortho hydrogen. But if it is opposite, it has nothing to do with electron. It is all about the proton, that is the nuclei we are talking about. Then if it is opposite spin, you will call it para hydrogen. Now when it is ordinary hydrogen that we deal, suppose we are doing any reaction in laboratory, ordinary hydrogen, what is the amount of these 2 form, what is the percentage? So they remain in equilibrium with each other. So there is equilibrium mixture of both the forms, and the conversion between these 2 forms, that is extremely low. So you can expect that their ratio, it will not change with time so easily, because conversion rate is low. Nuclear spin interacts so weakly with other properties of matter that these spin states are conserved in almost any process, including chemical reaction. Now suppose you have taken ortho hydrogen, you are doing some reaction with it, then there is some, that is, if you simply dealing with ordinary hydrogen, there is basically both the forms present. Now they are undergoing some chemical reaction. Now, chemical reaction, it is all occurring with the electrons. It has nothing to do with the nucleus. So that is why there is no direct effect on the nucleus. And ortho and para hydrogen, this definition is based on the nuclei, that is the direction of nuclei. But spin states are basically conserved in not just chemical reaction, in other processes also. Suppose you are simply heating it and then you are taking back to original temperature, or you are doing some chemical reaction, but it has nothing to do with the nucleus. So in most of the processes, nuclear spin, it interacts, its interaction with these external disturbances, it is not so high. So that is why it remains same. They can interconvert. Though we have seen there is equilibrium, their conversion rate naturally, if you are not doing externally any changes, naturally it is extremely low. But they can interconvert under certain condition, that is forcefully if we do make some changes. Suppose we are introducing some catalyst such as activated charcoal or various paramagnetic substances, then their conversion is possible, or by applying electrical discharge to hydrogen gas, or you are heating it to high temperature. So in all these cases, this equilibrium mixture, there is a fixed ratio. So you can change this ratio by doing all these processes. But we have to remember that the equilibrium shifts when you are lowering the temperature, the equilibrium shifts in favor of para hydrogen, where the spins are in opposite direction. But what about room temperature? At room temperature, ortho to para ratio This is basically 3:1. That means ortho form is high compared to para form. And when you are lowering it, this para form, this ratio, that will change because now the para form is more preferred. But don't think that when you are lowering temperature, so para will be more. So when you are making the temperature high, then the amount of ortho will be very high. But actually that doesn't happen. Even if you are increasing the temperature, the ratio, it never changes. That is more than this. So it is never 4:1 or 5:1. This is a maximum ratio possible, and in room temperature also this is the ratio. But if you decrease the temperature, then ortho amount may decrease and para amount it may increase. Chemical properties, it is same as I have said. It is the property of nucleus, and nucleus spin, it is not affected by the external whatever chemical processes are occurring. Chemical process is all about with electron. Boiling point, there is a slight difference. It is slightly less. That is the para form. This is also, that is melting point is also slightly less. But magnetic moment, it will be as both are in the same direction, so it is not cancelling each other. So that is why it is 0, but in this case it will be twice that of a proton. Proton means if you simply consider one H. So compared to this now, magnetic moment, because that depends on how many unpaired, that is not unpaired, I mean to say how many this type of atomic, that is proton, electron, neutron, different atomic particles. These are basically atomic particles. So magnetic moment, if you consider for the nuclei, it is basically twice that of proton, because both are in the same direction. But in this case, one will cancel the other. So ultimately magnetic moment will be 0 in case of para. So these are the, that is how we can compare the ortho hydrogen and para hydrogen. Preparation of hydrogen, how we can prepare it. But when we talk about preparation, there is two things. Laboratory preparation means small scale preparation that we can do in the laboratory. But when we are talking about commercial production or industrial preparation, that means we are producing it in large amount. So both these processes are obviously not same. First we will see how we can do it in the laboratory. It is usually prepared by the reaction of granulated zinc. So granulated zinc is very important here. We do not take pure zinc. We take granulated zinc in granule form, and they are not very pure. There is some impurity, and this impurity is basically desired because there is an impurity copper which acts as a catalyst. So better if you use granulated zinc. And we take dilute hydrochloric acid or H2O2. Remember, it should be dilute. It is very important that the acid is dilute. Why? We will also come to that point. So zinc should not be pure. It should be impure, granulated, and acid should be dilute. So here you can see the arrangement. We have taken this dilute hydrochloric acid, sorry, the spelling mistake, dilute HCl or H2SO4, and through this thistle funnel, this is a special design funnel. It doesn't look like normal funnel. We have to add this acid, and there is already zinc granules are zinc pieces mentioned there, that is present. So acid is added to this flux, which is already containing the zinc through a thistle funnel, and once it is in contact with the acid, then there will be formation of, so if I write the equation, balanced equation, it will be 2 HCl Zn, ZnCl2 and 2 hydrogen. So this hydrogen is basically, now it will see another outlet is there. So it is a delivery tube, and there is already water we have taken, and there is inverted, this type of a cylinder is there inverted. So these bubbles of hydrogen gases, gradually it will be deposited here. So this H2 gas that is produced in this reaction, it is going through this delivery tube, ultimately collected to this downward displacement of water. So what hydrogen is this gas, it is lighter, it will be deposited here. we have to keep these points in mind. We do not take concentrated HCl in the laboratory because they are very volatile, and when these hydrogen gases are produced as product, what will happen? Because of this volatile nature of concentrated HCl, they will also be mixed with this hydrogen gas, but that we do not want. We simply want pure H2 gas that we are producing. So that is why concentrated HCl is not taken. Concentrated H2SO4 is not taken, but now the reason is different. Concentrated H2SO4 is basically oxidizing in nature. When it is dilute form, oxidizing nature is not so high. So concentrated H2 being oxidizing in nature, there is a chance that the H2 that is formed, it will oxidize it to water. But that is obviously not desired. So that is why concentrated H2SO4 also we do not take. Then granulated zinc. Why we take it? One reason is obviously copper is present as impurity which acts as catalyst. There is another reason why granulated zinc is preferred over pure zinc. The reason is it has more surface area. So granulated zinc, it basically looks like this if you simply look at the granulated zinc. So there is surface area compared to pure zinc strip. Obviously it will be high. So these are the two reasons why we take granulated zinc. Higher surface area means because the reaction actually occurs in the surface of this metal. So more surface area the acid can come into contact, more will be the reaction. Okay. So in this way we produce hydrogen in the laboratory. When it is commercial production of H2, there is basically many methods that we discuss one by one. The first one that we are going to discuss is for large scale preparation is electrolysis of acidified water. Now electrolysis, if we want to understand in detail, basically electrochemistry you have to know, but that is present in that unit is present in class 12. So here we will try to understand the reaction as easily as possible. Electrolysis of acidified water. So here using electrical energy, basically from H2O we will try to produce hydrogen. And in electrolysis process there is a cathode and there is anode. In cathode there is a reduction occurring, in anode there is oxidation occurring. So cathode and anode, what are the reactions here going on, that you will see. Here the reaction that you are seeing here, that is actually the overall reaction. 2H2O, electrical energy, there will be formation of 2 hydrogen gas as well as O2. Bubbles of H2 form in the cathode. So this may be an important question. Suppose in the question if it is asking what is in which electrode cathode is formed, in which electrode hydrogen is formed, then the answer is it is bubbles of H2 form at the cathode and O2 evolves at the anode. So this is important information. So the individual reaction, if we see anode, there is remember electrolysis of water possible with acidified that is acidic medium as well as basic medium. So here we are talking about acidic condition. So H2 in anode, H2O is basically release electron. 2H plus half oxygen, I am writing the balanced equation, 2 electron. And in case of cathode, 2H plus will accept these 2 electron and it will be converted to H2. Now if you add these two reaction, half reaction, 2 electron will be cancelled, HH will be cancelled. Ultimately you will get H2O, half oxygen, hydrogen. If you simply multiply both sides with 2, you will get this equation. But if you that is multiply both sides with half, you will get this one. It doesn't matter, both are actually same. So these are the reactions going on. So you may get question from this, that when it is production of H2 by electrolysis of acidified water, what are the individual reactions going on in anode and cathode. This is the first method. Second method. Now this, remember this second method, it is special. Why we have to remember it especially? Because it is specially for the production of high purity hydrogen. In other methods also you will get pure hydrogen, but the purity level that is maximum in case of this second method. So that is why this second method, and based on this you may get question also, that is in which method pure hydrogen production is possible. And the answer is, again we will do electrolysis, but now warm aqueous barium hydroxide. Barium hydroxide is this molecule, BaOH whole 2. Barium is from group 2 alkaline earth metal between nickel electrodes. Now what are the reactions going on at anode and cathode, that we will see. So again you may get question, what are the reactions, individual reactions going on in cathode and anode. Now in anode, as it is barium hydroxide, and there is also, it is aqueous, that means the anion that is present in the medium is HO minus. So here HO minus, that will basically release electron because it is oxidation, so there will be removal of oxygen, removal of electron. And in the cathode, now you can say obviously it will be barium plus, but remember barium 2 plus. Remember, when you are doing electrolysis, there is basically two types of cations present. One is Ba2 plus, another one is H plus, which is coming from water. Now there is also H2O itself present. As we know, H2O, its dissociation to H plus and HO minus, it is not very high, so mostly it will remain as H2. Now there is, depending on the electrode potential value, for different system there is different electrode potential value. As I am saying, this is, if you want to understand in detail, basically electrochemistry knowledge we require, but that is in the higher grade, that is class 12. So that is why I am trying to explain it as easily as possible. So between barium 2 plus and H2O, H2O has more tendency to accept electron. So that is why here I will write H2O, and this H2O will accept electron. It is not barium 2 plus which will accept electron. It is H2O that will accept electron, and it will be converted to hydroxide ion. And sorry, one hydroxide ion and half hydrogen. Now if you add these, electron cancelled, these two are also cancelled. Ultimately you will get the equation, which is, sorry, 1 minute. So it is 2HO minus, let me write it freshly. Hydroxide ion, there will be electron release from this. This is balanced equation, 2 electrons. If we add it, electron cancel, hydroxide cancel, there will be 2 H2O, sorry, only 1 H2O, because there is 1 H2O in the right hand side, and here it is half oxygen and H2. Okay, so this is the overall equation. Basically the overall equation you will see it is same as the previous one, but individual reaction, if you see in cathode and anode, there is difference. Fine. So it is not barium 2 plus we will get reduced, it is water that will be reduced to HO minus. This is the second method. Remember, this method is especially important because only in this method you can get maximum pure H2. Then the third process, this is also basically electrolysis. H2 is obtained as a byproduct. Now it is not the main product. When we manufacture sodium hydroxide, basically this method is for the formation of NaOH, but byproduct is generated, which is H2. So what we do in this case, we do electrolysis of brine solution. Brine solution is saturated sodium chloride solution. So in this case, as there is presence of water, presence of Na and Cl. So the anions that are present, let me another color. So the cations that will be present is Na plus, H plus. Anions present Cl minus, HO minus. Now the tendency between Na plus and H plus, the tendency to accept electron compared to Na plus, the tendency to accept electron, it is more for water, even not H plus. So that we have also seen in the previous reaction. So that is why if you see at cathode, electron is accepted by water molecule and it is converted to HO minus and hydrogen gas. So this is the product that we want. And at anode, Cl minus, which is releasing electron. That means Cl minus is oxidized to Cl2. It is not HO minus which is oxidized. And how it is decided? It is all dependent on the electropotential values for individual system. So for Cl minus Cl2, this will be the reaction occurring, not HO minus will release electron. Cl minus, from Cl minus electron will be released and this electron will be accepted by water in the cathode. Now if we add these two equations, basically what will happen, H2 will be there, HO minus will also be there. Basically there is no species that will be cancelled except electron. So every species will be present. Now what we are doing, overall reaction. Now if you are thinking how NaOH will be produced, because this is the main product. Basically if we add the spectator ion, why I am saying spectator ion, because it has no direct role, both side it is present. So you can say why not cancel, but we will not cancel it, because once you write it, then you can get sodium chloride together and here it is sodium hydroxide together. So the overall reaction you can also write it like this, that is 2NaCl, it is reacting with 2 water, it is producing chlorine, it is producing hydrogen and it is producing NaOH. So that is why we have added spectator on both sides. So see here, main product is NaOH, but we can also get hydrogen as the byproduct. So this here may be a question, that in which method the byproduct is actually hydrogen, in which electrolysis, not the main product. Fine. Some more methods we will see for commercial production of hydrogen. This is only 3 methods, but these are not the 3 methods. There are more methods for large scale preparation that we will see in the next class. We are at the end of the session. Thank you for listening.